All right, so the formatting of this video is obviously very different than what you guys are used to seeing with these videos, but I wanted to give you guys a chance to look at a really kind of useful visual aid here that's going to guide our discussion of our new chapter on confidence intervals. This is an activity that I usually do in class where I call somebody up to the board and I use them as my visual aid. But I'm just going to do it myself here so you guys can get the same sort of impact out of that. So our concept or our context for this problem right here is looking at a situation where I would want to take an average of something. And what I'm going to use for my example right here is I'm going to look at the average number of social media posts that the teenager in the US views in a day. There is an actual number for that average. I could go to every single teenager in the US and I could look at how many posts have you guys looked at today on TikTok or ChatSnap or whatever it is that you guys are using these days. And I could get an actual number for that, right? If I do that, I would have mu. I could find the actual average for every single kid in America. Now, that would be fine and good, but obviously it's not very practical or worthwhile even to go and talk to every single kid and get that average. That's a lot of work and a lot of money going into an answer that's ultimately not super consequential. So instead of finding the real actual population average, what we do, as we've talked about already, is we use our statistic, which in this case would be X bar. So I'm going to use X bar to estimate mu, our actual population value. Now, the way that last chapter worked, chapter 7 on sampling distributions, we acted like we knew what mu was. We said, oh, assume mu is this number right here. And then we looked at how X bar sort of behaved. We have that stuff about it being approximately normal if conditions were met, et cetera, et cetera. But we acted like we knew the parameter. In real life, that's not going to work for us because we will not have access to this guy right here. We're trying to find this guy. But it's still worthwhile to do what we did last chapter because we learned how this guy right here actually behaves. So, going back to my example with the social media posts, I want you to picture like this wall behind me here is a number line. Way over at this end, we have a 0. So no average is 0 social media posts per day. And it goes all the way up to some giant number, whatever that may be. So we've got a number line right here. And mu actually does exist. There is an average that I could find if I talk to every single kid in America, but I don't know it. So I'm putting this on the wall right here to represent a point on the number line where the mean is, but I wouldn't have access to this if I am collecting data. All I would have access to is the sample mean. And I'm going to use my sample mean to try to predict what this value that I don't actually see is equal to. Okay? So what I would do is I would go out and I would scoop up however many people I'm going to use for my sample. And I would find the average. So I have a little sweet sign right here. This sign, I am X bar for this problem. Now keep in mind, 0 is way over here at this end of my number line. And then a million or whatever is way over on this end, and there's anywhere in between right here. If I take a sample average, the chances are I'm not going to get exactly right here. What are the odds that your sample mean is going to exactly equal your population mean? Probably not. Now, it's probably going to be reasonably close. I might be here, or I might be like here or something like that. But the odds of them exactly aligning is not very good at all. So what we do to kind of fix that or account for that, at least, is instead of just saying, oh, I think the answer is here, I think this is the actual mean, what we do is we give a range of values. So instead of saying, I think the actual average is 700, what I'll do is I'll say, oh, I think the actual average goes from 642 to 7 whatever, and I give a little range of values instead. That range of values is called a confidence interval. So what I want to do, instead of just guessing a point, this sign right here, my statistic in this problem, I am what's called a point estimate. I am the single best guess for what you think the answer is going to be, okay? So I am a point estimate. When I spread my arms out, though, what I get from here to here is a confidence interval. And a confidence interval says, hey, I'm pretty confident the actual average is between this point and this point right here. Now, when I'm making my estimate, I do have a decision that I have to make. And the decision is, how wide should I reach my arms? Should I say my interval goes from like here to here? Or should I say my interval goes from like here to here? I have kind of an impact or a decision to make in how wide I want that interval to be. So what we call the distance from the middle right here, from my estimate, to the edge, this distance is called the margin of error. It's like the maximum distance that I would be comfortable, like that my answer might be off by, okay? So I have a point estimate, I have a margin of error, and when I go both ways, I have a confidence interval. So there are two kind of factors at play when you talk about confidence intervals. One is you actually want to be correct, okay? If I say, oh, I think the interval is like here to here, and I'm standing way over here, well, I'm not catching the right answer. I didn't catch the right answer, so that's a bad thing. I'm more likely to catch the right answer if I reach my arms out nice and wide like this. Like that mean is underneath my arms right here. So I would catch it if this was my interval, or if this was my interval right here. So you have two factors at play. You don't want to miss the answer. But if you reach too wide, your interval is no longer helpful. Like if I go like this, I basically can be pretty sure that I caught the actual answer in my interval. But at the same time, if I say the average number of posts is somewhere between 0 and 1 million, or 5 and 700,000, or something like that, it doesn't really give you anything helpful. So as we progress through this chapter, you're going to have to kind of balance those two factors. I want to be correct and actually catch the answer that I'm supposed to catch. But I also want to make sure that when I make my interval, it's narrow enough that it actually still tells me something helpful.
Okay, so let's go ahead and tie together everything that I was talking about in my little demonstration there and get going with our actual notes for section 8.1a. As I said, the title of chapter 8 is the concept of confidence intervals. And in this section, what we're doing is we're learning the basics and just wrapping our heads around what a confidence interval actually is. How we make them and more complicated stuff like that comes later in the chapter. But your job in this lesson is basically learn the vocab and wrap your head around what a confidence interval is even trying to do. So I talked about this in my demonstration, but the difference between chapter 7 with sampling distributions and chapter 8, and actually the rest of second semester for that matter, is the idea that in chapter 7, we act like we know the parameter. So in chapter 7, we know the parameter. If you think about it, knowing the parameter is pretty unrealistic in real life. When we're doing a situation like with my example on average number of social media posts, I don't know the actual average, and I might never know the true average. It's not reasonable for me to have that information because I'd have to go to every single person out there and collect data from them. But chapter 7 is so huge and so important because when we assume we know our parameter, we get to see how our statistic behaves. We get to see what kind of shape it has. We can find probabilities related to it. We learn a lot about X bar, about P hat, and about our other statistics, which we're going to take that info and use it the rest of the semester. But it's starting in chapter 8. This is where things sort of get real, in the sense that we won't know our parameter anymore. So beginning with chapter 8, we don't know the parameter, and we're actually trying to find it. So that is what we're trying to do in chapter 8. We want to use our information that we have, which is mostly just going to be our statistic, what we get from our sample. And we're trying to figure out what that actual parameter is equal to. So we talked about a bunch of vocabulary earlier, and I'm going to go ahead and put definitions up here and talk you through a few reminders regarding them. But this is all vocab I covered in my demonstration. All right, so here are some definitions to the vocab terms that I talked about in my video. And as you guys are writing these down, I'm just going to talk you through a few highlights regarding this. Remember, the point estimate is just your best guess for what you think the parameter is going to be. And usually you just use common sense when you're deciding your point estimate. You use the statistic version of the parameter that you want. So if you're doing a problem on mu, well, x bar is the logical choice for your point estimate. If you're doing a p problem, you would use p hat as your estimate, and if it's sigma, you would use s. So you start out with the statistic. If you had to guess something, you would guess that statistic. But as I said, if this is my parameter, the chances of my statistic perfectly matching up with it, not very good. It's more likely that I'm a little bit off. I'm probably close, but I'm probably not exact. So what we do to account for that is, instead of a single guess, we build a margin of error around our point estimates. So here's my point estimate right here. I spread out my arms and I say, I think the answer is in this range, or this range, or this range. And that is called a confidence interval. So a confidence interval is just a range of plausible values for the parameter you're trying to estimate. And when you build a confidence interval, we're going to learn later in the chapter formulas for actually constructing our own. But for now, our basic setup is just you start with your point estimate and you add and subtract a margin of error. The margin of error is the distance from the middle of your interval to the edge, and it represents the maximum amount you feel your answer might be off by from the parameter. So yeah, that's all vocab that we talked about, and hopefully that visual aid is helpful to you guys. On this slide, we talked about two factors that are important to consider when you decide how wide your interval is going to be. You need to make sure that your interval actually catches the answer it's supposed to. You want it to be factually correct, but you also want it to be narrow enough that it's still helpful. So we got a sweet Garfield comic here on the bottom of this slide that illustrates that point perfectly. Garfield's looking at the weather, and the weather person is like, hey, the weather for tomorrow is going to be between -40 Fahrenheit and +200 Fahrenheit. And Garfield just kind of chuckles and said, man, this guy's never wrong. So while it's true that the weather person is never wrong in this situation, they're also not conveying any useful information. If it's -40 outside, I am not leaving the house no matter what. If it's 0, if it's 30 or something like that, I'm wearing a thick coat. If it's 90, I'm wearing shorts. If it's 190, I'm not going outside because everything is probably almost melting. So you have no information to move forward with. So you want to make sure your interval is narrow enough that it's still helpful while being accurate. So the purpose of this slide right here, we are actually going to learn a very important script. A big part of this chapter and of AP Stats in general is learning scripts for how you interpret different pieces of information. So put a star at the top of this page. This is going to be a script that we can use to interpret a confidence interval. So if we actually needed to talk about what a confidence interval tells us, this is what we would do. So to quickly summarize what this problem is about, this is a relatively recent survey from October 2019 by Pew Research, which is a really famous, really important research company that does a lot of polling, so surveys and that sort of thing. They looked at, in America, at what people thought about how we are handling climate change, the issue of climate change, and basically whether our country was already doing enough to combat climate change. So they talked to 3627 American adults, presumably randomly selected, and they asked if they felt we were doing enough as a country to combat climate change. So what they looked at was the percent of people who did not think we were doing enough. Okay, so they looked at the percent of people who didn't think we were doing enough, and they got the following confidence interval right here. So one way that you can write a confidence interval is like this: number plus or minus number. And as I showed you earlier, this is the point estimate, and this is the margin of error right here. So we have point estimates, and we have margin of error. So what this tells me, when I see this result right there, is when they talk to their 3,600 people, in their group, 67% said, no, we're not doing enough. So the point estimate is probably what they actually got from their survey. But then they did fancy math that we haven't learned yet, and they built this margin of error, which says, hey, my 67% could be off by as much as 1.5% in either direction. Okay? Where the 1.5 comes from, we'll talk about later. But for right now, we need to figure out, first of all, what this does for us. Before I get to that, in a typical survey, high-powered survey from one of these research companies, you'll generally see margin of error in the 3 to 4% range. That's a pretty typical polling error. This is actually a fair amount smaller than what you would typically see. The reason for that is this is actually a bigger group of people than I usually see in your standard survey. Most surveys that are posted online have 1,000, 2,000, even less than that people who were surveyed. This is actually relatively large by talking to 3,600 people. You actually don't need to talk to a super ton of people to get really accurate results in polling. So they talk to their 3,600 people and they find this interval. Now, while that is fine and good, you guys will usually be expected to write an interval in interval notation like you would have learned in Algebra 2 or Pre-Calc or something like that, where you put your low number and your high number in interval notation. So all I'm going to do with that, generally we don't like to use percentages. We like to turn them into decimals. I'm just going to take my point estimate and I'm going to add and subtract my margin of error. If you do that, the low end is going to go 0.655 and the high end is going to go 0.685. So what does that mean? Well, it means we're pretty confident the actual percent of people who are not thinking we did enough with climate change is between a 65 and a 68%. Now, there's an actual script that I want you to use that fully interprets this for us. So I'm going to write that up there and then we'll talk about it. All right, so here at the bottom, we've got ourselves a little script that I want you to kind of use and learn for interpreting a confidence interval. And what I said is that we are 95% confident that the interval from 65.5 to 68.5% captures the true proportion of US adults who feel we are not doing enough to address climate change. So when you're looking at this as a script, there are 3 things you're going to change. One is going to be the confidence level. This was a 95% confidence interval. We could do a 90, we could do a 99. You can have different percentages for your confidence interval. We're going to learn what that means in the next slide or two. But when you do confidence intervals, you'll want the percent to be high. You're not going to make something stupid like a 20% confidence interval because it gives you virtually no information. So you decide on your confidence level right here. You give the actual interval from the problem, so that'll obviously change, and then you talk about context when you're writing out your answer. So those are kind of the 3 pieces that will change when you write one of these out. But this is a script that you can use anytime I ask you to interpret a confidence interval. So we're going to move now, and we are going to look at the idea of a confidence level. And in order to do that, I have a sweet internet applet right here on that'll help us kind of figure out what's going on. So the way that this internet applet here actually works is over here on the side, you'll see where this pi is. Pi, remember I told you last chapter, is the Greek letter for P. So sometimes they use a pi, which is kind of confusing, so we don't do that. We just use regular P. But let's look at a situation where the actual percentage we're trying to estimate ends up being a 0.6. We're doing samples of size 100, and I'm going to generate one interval right here. And we're doing it at a 95% confidence level. So let me go ahead and generate a sample and show you how this works. So let's go with this one right here. If you look at this little setup right here for my interval, there is a dot in the middle of that. That dot underneath or above my mouse is our point estimate. That's where I would be standing in this problem. So the real answer is a 60%. I scooped up a sample, and apparently I got a 66% for my p-hat in this problem. But even though I didn't actually catch, I wasn't the right answer. 66% isn't the correct answer. When I spread my arms, I still was able to catch the real answer of 0.6, which is this line right here. So that interval is still considered a success because it captured the right answer within its range. If I make another interval right here, this one was a little lower for my answer. I got 63%, but that person still caught the right answer. We're good to go. And it just keeps on going like this. Now let me find one where it doesn't work. All right, eventually it's gonna miss. Oh, I saw a red one. Okay, whatever, I missed it. If my answer is too far off, like if I get a 50% or something like that, then even when I reach out my arms, I can't reach that 0.6 like I'm supposed to. So I could capture the right answer within my range, and it'll show up green if that's the case, or I'll miss and it's red. So what I'm going to do now, instead of doing one at a time, is I'm actually going to change this so it does 100 at a time. So it's going to make 100 different confidence intervals right there. So you, me, and 98 of our friends are all going to take our own separate sample, and we're going to figure out our own percentage. So you're this very first dot right here, you got like a 57% or something like that. But even though you were lower than the real answer, when you reached out your arms, you were still cool. I was the next dot right here. I got like a 66%, but when I reached out my arms, I was still good. And we go down to our friend over here, this red line. They ended up somewhere in the neighborhood of like a 48 to 50%. And when they reached out their arms, they still didn't catch the right answer. It's not their fault. They didn't mess up or do anything wrong. It's just sometimes when you pull a sample, you get like an odd, fluky sample that doesn't match the real answer. If the real answer is 60, you could get, in theory, a 50 or a 40% for your group. So what would happen then is you would have a misinterpretation, or you would think you knew where the answer was, but you wouldn't be correct. Okay? So in this batch of 100 people, we did this 100 separate samples. 97 of us caught the right answer. Okay? So we have a 97% success rate in that group of 100. If I do it again, here's another batch of 100. I got another 97 for that one. If I do it again, there's a lot more people who missed this time. So that group only had 93% of their people who got the right answer. And we're just going to do this a bunch of times right here. And we're going to look at the running total for what percent of the time overall we've caught the right answer. Okay, so far I've done just over 1,000 of these, and I've found that approximately 95% of them capture the true answer. And that's actually what ends up happening if you do enough of these. If you do tons of different intervals, you take one, I take one, we make our intervals, 95% of the time we'll capture the right answer. Okay? So I'm going to change this number right here from a 95% to a 99%. And before I do this, I want you to predict if those little intervals right there are going to get bigger or if they're going to get smaller. Will they get wider or narrower when I change this to a 99? And if I actually do it, you'll see that they totally got wider right there. Why does it make sense that they'd be wider? Well, now instead of 95% of our different samples working out, we want 99 of them to work out. And if it's 99% a higher percentage, it's going to get wider to compensate for that. If I lower this guy to like a 90, well, now you're going to see them shrink quite a bit because only 90% of them are going to capture the right answer. So that's the idea behind a confidence level. So how do you actually go ahead and interpret a confidence level? You're going to talk about how over many random samples, what's going to happen. So over many random samples, approximately 95% of the intervals generated from those samples will capture the true parameter. Sometimes I word it the other way. Like I might say something to the effect of, if we take many samples and generate many confidence intervals, approximately 95% of them will capture the true parameter. This is going to be another script. This is for a confidence level, where the last one was for a confidence interval. and you'll be expected to be able to handle both of those situations. The idea is if you make lots of intervals, about X% of them will capture the right answer. One side note here, which is kind of important, when you talk about confidence levels and stuff like that, avoid mentioning probability. AP rubrics will take off if you talk about, oh, it's a 95% chance that it's going to capture the right answer. That is considered not so good because in theory, the answer already exists. It either is or it isn't captured. It's not like basically just avoid probability. It's a weird technicality, even though it sort of maybe makes sense in your head. Don't talk about confidence intervals in terms of probability. Talk about how if you do lots of them, this certain percentage of them will capture the right answer. And then we're going to close out this lesson with a big example right here where we get to do all the stuff we've been practicing. This time, we're making an interval for the number of steps taken in a day by different employees at this company. And they make their 99% confidence interval this time. Last time it was 95, so now it's 99. They find their interval to go from here to here. Okay? So we are trying to find the average number of steps, and we believe this average is in this fairly large range right here. The first thing they ask us to do is interpret the confidence level. The level is the percentage. It's the 99%. So if we took many random samples and generated many confidence intervals, CI is a appropriate abbreviation for confidence interval that you can use. So if we took many random samples and generated many confidence intervals, approximately 99% of the intervals created would capture the true average. So about 99% of the intervals that we make are going to catch the actual average, whatever it may be. All right, next up, they ask us to interpret the confidence interval. This is the other script that I taught you guys with the we are blank percent confident. So I'm going to say it, and then I'll write it down to save a little bit of time in this video. We are 99% confident that the interval from 4547 to 8473 captures the true average number of steps by employees at this company. So I'll put that down for you. All right, so there is the script written out for you guys there, how you interpret your confidence interval. So we're pretty sure the answer is from 4547 to 8473. If we wanted a narrower interval, so it'd be a little more helpful, there are things we can do, and we'll get into that as the chapter progresses. So 2 more things I have for you guys, and then we're done with this lesson here. The next thing they ask us to do is actually calculate the point estimates and the margin of error. So our interval from the last page went from 4547 to 8473. So this, if you think back to my example way back when I started this lesson, the point estimate is the middle of your interval, and then it goes from here to here. So if I were to average these 2 numbers and find the midpoint between them, that would exactly be my point estimates. So my point estimate is going to be, I'm just going to add these up, and after I add them up, I'm going to divide by 2. If you do that, you get 6510 for your point estimate. So that must have been their X bar, their average when they did their 50 employees and took their average in the study. The margin of error goes from the middle to the edge of your interval. So all I'm going to do is take my middle right here and subtract one of these. Doesn't even matter which one. If I subtract this number right here, 8473 minus 6510, that is a margin of error of 1963. So it's not that bad to find these things algebraically if you understand what they're saying. All right, last thing. Recent guidelines suggest for people that they should aim for 10,000 steps per day. Is there convincing evidence that the employees of this company are not meeting the guideline on average? Okay. So it's supposed to be, we're hoping we're at 10,000. We're really confident the answer is in this range right here. So something you'll be asked to do a lot with confidence interval problems is make a decision or make a conclusion based on them. Look and see if the number we care about is in our interval. So since 10,000 is not in the interval, we're pretty sure the answer is not 10,000. So I'm going to write that down and give you guys that in just a second. You'll have a nice formalized answer. But if the number we're looking for isn't in the interval, we can rule that number out. I want to talk about one more quick thing. And let's say they said, oh, the actual goal is 8,000. So 8,000 instead of 10,000. Should we be confident we're meeting our goal? And the answer to that question is different than the question that's actually typed up right here. 8,000 is in that interval, but there's also plenty of stuff that's less than 8,000. Okay? So if the question said 5,000, can we be sure 5,000 is the answer? There's still stuff that's less than 5,000 in our interval. So if they said, oh, can we be sure the average is 5,000 or 8,000? We'd be like, ooh, I can't really tell. There's stuff that's below it in the interval too. The only time I could say like, yes, I'm sure, is if they asked about like 4,000. Can we say the average is above 4,000? Yes, we can. Can we say it's above 5,000 or 7,000? No, we can't, because there are numbers in between that range. So the way you address one of these questions is different depending on what it is you're trying to do. So I'll put up an answer for what they actually asked right there, and that'll be our lesson. All right, so recapping what I just said, 10,000, all the numbers that we think the answer might be are below 10,000. So we're pretty sure the average for our company is below 10,000. Now, it's really important when you talk about these that I mention on average right here. There totally could be, and probably are, employees at the company who by themselves are beating the goal. There are probably some people in this company above 10,000, but the average of all employees, we're pretty sure, is below 10,000. So that difference is really key.